Hi, my name is Chris Kopacz. This is my final project presentation for CS89 Deep Learning in the fall 2024 semester. My project topic is image colorization. Image colorization, in the strictest sense, is taking an image that either had color and lost it or never had color, and applying what a neural network is trained to think the image might look like with color. It's used in historical image restoration, medical imaging, entertainment. It's used in law enforcement and forensics with things like security camera footage. It appears in a number of different places throughout the world. My use case is a much simpler example. I started by training the models on basic shapes where circles and ovals are always green, triangles are always blue, and squares are always red, just to verify that the architectures that I had decided on actually could work. And then from there, I implemented a much larger data set of images from different cartoon television shows. Um, I ended up with five different models. Only four of them are really studied for this project. The fifth model is an implementation of the PIX2PIX GAN. I just wanted to compare the output of that final fifth model to what I was getting with the other four because I knew that the GAN would produce pretty incredible results, and I wasn't sure what the other models would do. As for the other four models, I had a baseline, which was the simplest, most straightforward um, implementation of a convolutional autoencoder. Nothing fancy about it. It just takes in images and tries to predict the colors in the simplest way possible. Um, the other three models, model two, three, and four, for the encoder portion of the model, overall model, um, the encoder is replaced with a pre-trained base model that's open source. Model 2 is VGG19. Model 3 is ResNet 50, and Model 4 uses Exception as the base model for the encoder. The baseline model, as I mentioned before, it's just straightforward. I wanted to see how long it would take to train a model from scratch, and how well it would perform just in kind of its simplest form. Overall, it definitely took the longest. With 25 epochs, it was almost 3 hours in training time. Um, and as far as performance goes, as expected, it basically performed the worst. Shapes it handled relatively well. Um, but then stepping into the cartoon image colorization, the results were all over the place. The images often resulted in very splotchy or patchy colorizations. The colors were usually wrong. Um, for the second model, using VGG19, this is the closest to the baseline in terms of architecture. It's just a much deeper uh, convolutional encoder. It handled the shapes perfectly. And then for training with the cartoon image data, the best results, and this is true for models 2, 3, and 4. If I train the models on a data set with images from a single show, say, for example, only Smurfs, um, the results were pretty decent. But if I trained with a data set that pulled images from a number of different television shows, um, those predicted colorizations uh, suffered greatly in performance. They were pretty bad. VGG19 was the second slowest um, model that I trained at 2 hours. It's important to note for models 2, 3, and 4, the time for the Smurfs only training will always be longer than the multiple shows training. And this is because I accidentally used a larger data set for the Smurfs only. I think there were 2,500 images in the Smurfs only, and then only 2,000 in the multiple shows data set. Each of the models was trained with 25 epochs, though. Um, ResNet 50, in terms of architecture, starts to step away from the simple convolutional implementation from the previous two models. It uses skip connections between the convolutional layers so that um, the problem of disappearing gradient is handled. Um, the training time for this model was drastically reduced compared to the previous two, but also yielded similar results. When trained on only Smurfs, the results were pretty spot on, but then once trained on a data set that included images from multiple TV shows, um, it performed pretty poorly. The last model used exception as its backbone. Um, Overall, the time to train it was comparable to um, ResNet. Um, the architecture of this model again steps away from the simple implementation of straightforward convolutional layers and pieces it out into depth-wise separable convolutions um, so that each filter is handling a separate convolution on a separate layer. Overall, this means that the uh, this model ends up being the least complex in terms of number of trainable parameters, um, and without sacrificing performance in the end. Um, this model, when trained on only Smurfs, performed the best. It was the least patchy, the least splotchy, and the colors were the most accurate throughout. But again, it suffered the same issue when trained on images from multiple TV shows. The performance degraded drastically. The last model, Model 5, is just a PIX2PIX GAN. I didn't change this or modify it in any way. I just wanted to see how it would perform compared to the previous models when trained on images from one data set versus images from multiple TV shows. And overall, uh, as expected, this model performed the best across the board. It took the same amount of time to train with double the number of epochs, and the results for the uniform data set uh, were essentially perfect. And then the results for images from multiple TV shows were also nearly perfect, with the exception of some strange highlighting that appeared every now and then on certain images. Um, some comments to note about uh, the project overall and considerations for the data set. Um, this data set is a little strange. It pulls images from TV shows in assuming approximately 1 second increments. So if there are about 30 frames in 1 second on a TV show, you end up with 30 images that are nearly identical. It just requires further consideration when sampling the data for a training set or a test set, um, to make sure that you're not feeding in a ton of images that basically look exactly the same. The data set itself is about 12 gigabytes in size. Um, so I did run into memory issues when training. I had to shrink that down from many tens of thousands of images to 2 to 3,000, 5,000 at the most, in order to train these models. Um, if I had to pick a best, I would say that um, for models one, two, three, and four, number four performed the best. It was just the most consistent when trained on um, images from a single TV show. Um, Overall, models one, two, and three, one, two, three, and four all failed when training on images for multiple TV shows, and the GAN performed the best all around, but it wasn't really the focus of my project.